So here is the algorithm for solving these things, okay, is that the first step is to reduce the circuit until, this is a condition, right? I'm writing a computer program here, right? Until it's solvable. Is that how you spell solvable? Solvable. Is that right? Reduce it until it's solvable. Okay. Step 2. Okay. Solve it. Okay. Using either a series or parallel algorithm that you now know by heart. They're all series circuits are solved the same way. All parallel ones are solved the same way, right? Okay. Now, once you've done that, right? Eventually, you're gonna actually in this step you're gonna actually be able to read some of the readings on the voltmeters and stuff like that, right? Okay. But some of them you still won't know, and that's because you've reduced them. They are reduced things that we've taken a bunch of resistors and made them into one. You know what I mean? Okay. So for every reduced, in other words, every resistor that's not really one resistor but is actually many, okay, for every single one of those, find the voltage across it. Yeah? Find the voltage across every reduced circuit, okay, and then solve it like Beckham. No. Solve it like a circuit. Okay? Okay? So the name of this thing is circuit. Okay? So where do we do? Well, we go back to here, right? Okay? Yeah? So what we're going to do is we're going to take those reduced ones, unpack them, and then just solve them. Right? Now the trick here is, of course, you're not going to unpack it all the way and then start all over reducing it, right? You're just going to sort of pop it up one level and go, okay, now what is it, right? And I'll show you this, right? Okay. So for every reduced circuit, find the voltage across it. The voltage across this circuit is 17 volts, yes? Okay. But when we get down into the circuit, we're going to have all sorts of weird voltages or whatever, okay? And we're just going to take those things that we've reduced and pretend like there's a battery across it. Yeah? I'll show you. Okay, we're just to pretend there's a battery across it and that it's a separate circuit. We can ignore the rest of the circuit once we know the voltage that's across it. So let me just show you this in one of these. So I can't solve this circuit. It's neither series nor parallel, so I reduce the circuit, right? This one has one reduction, right? And we go 1 over 12 plus 1 over 24. And that was 8 ohms, wasn't it? Is that right? Yeah. Okay. And now this is a solvable circuit. I'm not going to reduce it into one resistor because I don't need to. It's a series circuit, isn't it? And I can solve series circuits. Step 1, find the current. So it's 17 divided by 5 plus 8 plus 7, right? Well, 5 plus 8 plus 7 is that 20? 17 divided by 5 plus 8 plus 7. That's 0.85 amps. Yeah? And I could store that somewhere, but this one comes out so even that I don't even need to, right? Okay? Does everybody else get that? Am I on the right track? Okay. Good enough, right? So now the next step is, let's see, solve it, series of parallel. Okay, so the next step is, I'm going to find let's suppose there was a voltmeter across this one here, right? The voltage across this one would be 5 times 0.85. Right, so we do the voltage is IR, right? I already showed you that, so I don't feel like, but I think I should put it up there again, right? So it's 0.85 times 5. That voltage is 4.25 volts. And the current through that one is, of course, 0.85. And that resistor, there's nothing more we need to know about it. We know the voltage, the resistance, the current, right? This one's easy. This one's easy. It's 7 times 0.85, right? V is IR. Is 0.85 times 7. So 5.95 volts is across that one. The current is 0.85 amps. Again, I know everything about that one, right? And now the exciting conclusion here is that I'm going to find the voltage for every reduced resistor, is the missing word there. For every reduced resistor, find the voltage across it. So I'm going to find the voltage across this one. Yeah? All right, so that voltage is going to be, well, I treat it as one resistor. It's just an 8 ohm resistor in a series circuit, right? Even though it's confusing, that's all it is, yes? Picture that in your mind. It is one resistor. Okay, so this voltage is equal to, across the reduced circuit, right, is equal to 8 times 0.85. Again, I'm just doing R times I, right? So 8 times 0.85, and I've got 6.8 volts. Okay? Now, for every reduced resistor, find the voltage across it, solve it like a circuit. Here's what I mean by that, okay? I take that circuit and I redraw it if I need to, okay? So now I've got what kind of a battery? I've got a 6.8 volt battery, and I've got a circuit like this. That's interesting. Isn't that interesting? Yeah. If I take this part of the circuit here and I apply 6.8 volts across it, I can remove the rest of the circuit. This is kind of a cool thing, right? If I've got a voltage source and I turn it up, if I measure this voltage or calculate what it is, and I turn that thing up to 6.8 volts and I connect it right there, at first it doesn't do anything, but then I can disconnect the entire rest of the circuit. And everything inside that circuit stays exactly the same. Isn't that wild? This is called Murray's theorem, right? Okay. This is how, see, alarm systems in houses, okay, alarm systems in houses, that's what they do. They've got resistors at the ends of, they've got these sensors that sense the door, right? Okay. Then they also have a way to detect whether somebody cuts the wire. And that is at the end of every circuit, they've got a resistor. And basically all alarm systems do is look for a change in the current. If the current changes, somebody did something and they shouldn't have done something because they haven't entered a code, so it sends off an alarm, yes? Right? So if you could get in there into that circuit, and like maybe this is the front door and the back door or something like that, right? Okay, and this is the something sensor or whatever, right? Or maybe it's sensing on this circuit. If you just get in there and take all the little things, bring a bunch of little voltage sources, and measure all the potentials at all the terminals that it's reading, and stick a voltmeter or a thing on there at that voltage, right? Okay, then you can just remove the rest of the circuit. The alarm's not going to know. Am I telling you how to defeat an alarm? Yeah, probably, but probably they've got fancy digital ones now. These are old analog alarms. I bet they've got fancy digital ones that have microchips at the end that send encoded things, or who knows, right? Okay, but real simple alarm systems, that's all they're doing. And if you stick, the point here is if I stick 6.8 volts across this, like this, the currents in here stay the same. So what kind of circuit is that? Now it's okay, so now solve it like a circuit. We're going to apply the general algorithm to that circuit. Well, do we need to reduce that to solve it? No, it evaluates as true. It's solvable immediately, right? Okay, so let's solve it. What kind of circuit is it? It's a parallel circuit. Okay, and so the current this way, let's draw the currents. Here's one current, right? Here's another current. Okay, the voltage across each one of these, is 6.8 volts, right? And the current on this one is 6.8 divided by 12, and the current on this one is 6.8 divided by 24. Okay. And so these currents are .566 repeating, right? And then the current on this one is going to be half that, right? 0.283, right? And then what are those going to add up to? What's that and that one going to add up to? Any guesses? 0.85. Somebody said 0.85. There we go. Why is it going to add up to 0.85? Because take a look at this. Let me change colors here. Right? Let me change colors here. But 0.85 amps is going this way, right?